So as I said, like 1 year and a half ago, I started studying why, if there is a pattern that can be followed in order to obtain equalization of the forces on every branch of the anchors. And we can ask in this presentation this question: why is it important to do so? And then I started studying symmetric anchors with 2, 3, and 4 branches, and the asymmetric anchors that has 2 and 3 branches for starting. I will develop more in the future. And then we will talk about what to remember about this thing, because the main important things when we look at an anchor, what to think, what is the branch that will suffer the most force, what is the bolt most likely to blow, and etc. So why is important? Here, please don't get distracted by Syria Zaro. That is when we were on a trip in Liguria. And why is important? First, for the knowledge of the phenomenon, because understanding the physical phenomenon, all the laws behind it, is the first thing to then study it and trying to do our best to improve. Then naturally for safety in our sport, because knowing how to properly place bolts, we can then know, as I said, which branches in existing anchors suffer the most forces, or how to obtain equalization. Naturally, all this in an ideal world where we can drill where we like.
Lorenzo, I think your slides are not moving. Could you maybe try to make your presentation full screen? We can still only see the first slide.
Okay. You see it like that? Different slides?
Now we can see the second slide.
Okay, okay. I will do it like that because in full screen there's some problems. Okay?
Perfect.
Okay. So as I said, I was only saying that this is the index of the presentation and blah, blah, what I already said. And we were talking why it's important. And the reason why it's important, knowledge and safety. And safety not only for the next bolting, for the next anchors that will come, but also for the existing one to assess if they are good, if there is a good bolting, or there is maybe one branch that is suffering all the loads and the others that are clearly have a really low force on them. And then for redundancy, that is strictly related to safety, because then we can know if there is an anchor that is already built, that there's a bolt that suffers a lot of force, but we cannot rebolt to back up firmly that bolt, and which are the forces that it will suffer. And during this study, I started easy, and wanted to study symmetric anchors. And for symmetric anchors, you have to imagine like a perfect flat surface. Imagine a canyon, a highline hanging on the ledge of this canyon. And so you have perfectly plain surface. And in this symmetric anchors, remember, it's an ideal study. Then we will talk about real case scenario. But in this ideal study, imagine there's a guy walking on the line, so not taking leash fall, no sudden forces, no surfing, no bouncing. Let's imagine that the tension is a constant value, because we are analyzing it as a static anchor. The anchors that I studied in these symmetric cases are 3, with 2 branches, 3 branches, and 4 branches. You can see with the dashed line the unloaded anchor, while with the full line, the loaded anchor. You can see that there's a displacement. Here is really big, but only to being able to see it. Not normally is not that big. But the key of my work was to find equalization in all the cases, but also the real forces that were taken by the bolts. Because maybe you all see the famous graph that shows you that the force that an anchor is holding increase with this angle, the angle between the branches. And there is like a maximum, this is infinity. When you have a 180 degrees angle, the graph says to you, okay, you have infinite force. That is not true, because in reality, you have the elastic component of the anchor. And due to this elasticity, the anchor is not 180 degrees, but it becomes a little less than 180. So you never reach infinite force. So starting from that, I said, okay, what happens in this ideal world where everything is static and cannot stretch and you reach infinity? While in the real world, you don't reach infinity, but you reach, independent of three factors, a top force. And these three factors that are really important for all the anchors are these: geometry, so how many branches, where you bolted, how long every branch is, so the geometry. The second is the elasticity of the material, so if you use a sling, a rope, a climbing rope. And the last, the tension applied. Why is this? Because the more the tension applied, the more the anchor stretch. And so the more the angle at the top it's reduced. The more is elastic is the same. The more material is elastic, the more it can stretch. So the angle at the top can reduce. And with the geometry, well, you can tell it that if you have a bigger angle or a smaller angle or 3 or 4 branches, the outcome will be different. But the important thing that was discovered was not about the 2 points anchor system, because it's always equalized. That's nothing to say. It's always equalized. The minimum angle that you can reach, the better. In the 3 branches case, that was when things became interesting, because it turns out that you can equalize every symmetric anchor, symmetric. Let's keep in mind that you can always equalize a symmetric anchor with any branches. And the key is that the more the branch, for example, let's take the 3 branches anchor, the branch in the middle has to be longer than the branches that are the lateral ones. Why is that? Because, as I said, the more the angle is open, more the strength these branches will carry. But with a third branch that is aligned, all this branch, the middle one, will take the most load. So if you have this branch that has the most load and these 2 that has less loads, the only way to make it even is to make it longer, like a longer spring. There is a correlation between that. I can show you, yes. For example, it would be nice to develop an app or a program that tells to you, for example, oh, I have 3 meters round sling. I want to make the anchor 2 bolts here and here. Where should I put the third one? Well, for example, I don't want to annoy you with graphs, but this is for example, an example of a 3 meter sling. They say to you, okay, I have a 3 meter sling. There is the distance between the side bolts. Where should I put downside to this imaginary line that unite the 2 bolts, the third bolt? Where should I put it? Well, in order to obtain equalization, as I said, it should be longer. And how much longer? This longer. You just find the distance and you find how much you must do longer this piece. Why this is not start from 0? Well, because I assume that you cannot bolt 20 centimeter close, more than less than 20 centimeter close, one bolt from one another. And also, why this one stops here? Because I assume that after 80 degrees, and I will show you later why, after 80 degrees, you should never do, not you should never do, you can do, but these laws are not valid anymore. So this, the big thing, let's say that you can always equalize an anchor, a symmetric anchor, but you have to remember that the internal branches, the more branches you have, the more internal they are, they have to be longer, like following a curve, let's say. So also for the 4 branches anchor, you will be always less force on each branch because you are dividing the total load, the tension, by more branches, but you also to have longer branches. This is the key. Then, while talking with Thomas, we started to think, yes, but what asymmetric anchors? What happens when you have anchors, for example, the hanging on the side of a ledge, the one that Sarah was talking about before? These are really tricky ones because, as you can see, imagine that this plane is the side of the ledge. You have a tension pulling sideways. They are not symmetric. And in this case, this anchor, you can tell by yourself, could never be equalized. You will never have equalization. The more you go further, you go away from equalization, from a symmetric pattern, the more you go away from equalization. But we have to say that that is not the only problem. The other problem is that as the highliner works, this anchor changes shape because we are talking about sliding X in this case. Sliding X with no friction, so this is ideal. So imagine that also if you have a little force in another direction than the perfectly planar like this, it will rotate a little bit, so it will start to rotate. And we all, I think, experience what happens when you work in such anchor that it start maybe there's friction that holds the binar, the shackle, and then all of a sudden it slips a little bit, and then another little bit, and then another little bit. And we were studying with Thomas which is the best way to bolt in this case in order to minimize this big slippage and also to have a good force held by each branch. And for example, you can see the next slide. We can treat also a special case that it happened to me not quite often, but a lot of times where you have, imagine a tree in the point A and another tree in the point B that you use because you don't trust enough. Maybe it's too little, the tree in point A, and you use another one that is slightly in the back, and you obtain this shape of the anchor. In this case, you have zero angle, so you would have the best force on each branch possible, but due to the different length, you wouldn't have 50-50 like in a ideal world, but you would have the short branch carrying more load than the longer branch. And this increases a lot as you have a difference in the length of the two. For example, if you have the longer branch that is double the length of the shorter branch, you have a difference that is like, I would say 70-30. 70% on the short branch of force, 30% on the shorter branch, on the longer branch. So let's keep in mind that this could be a viable option also in this case, but we have to study, maybe there's a better one, maybe there's a shape of a triangle or a distance that we can reach to have the minimum slippage of the shackle. For example, in this case, you could have minimum slippage of the shackle, but also little force. Then I wanted to be more redundant and study the third branch, the three-branch asymmetric anchor. And this was really something because it was, I encountered something called the trifocal ellipse, so like an ellipse with three foci, and it has a lot of equations and a lot of math, and it was really difficult. But the good news is that you can equalize this thing, you can equalize it, but it's really difficult, and I think it has not much interest, because equalize this thing is really difficult, and you will have to plan where to bolt, knowing the length of your sling and everything. But I have still to study that in order to do a program to do that. But I would say that this guy over here is really interesting also because you can put more and more branches, and you can use this law also with a small, when there are small angles. And so, of all that I said, there's something to remember. Like, I'm not giving you formulae or programs to calculate, because not every one of us will take the formula out on the highliner anchor. That's is not useful. The most useful thing has to be some rules in our mind to follow, and to know what to expect in case we encounter certain patterns. So these are what I call the Uncross 7 deadly sins, because all anchors do that. And so we have to keep in mind that the first thing that we see is alignment, and the more an anchor branch is aligned with the tension direction line, the higher the percentage of the total load it will carry. So in this case, if you have a branch that is more aligned with in this case, let's say, this branch, the middle one, is more aligned with respect to the tension direction line. So it will carry more load. The percentage, for example, imagine 60%, 30, and 10. Then there is the length factor, because the longer one branch is with respect to the others, naturally, the lower the percentage of the total load. So as you can see also in this case, this is the longest branch, and it will carry less load than the shorter one. Then we have elasticity and tension, because as I said at the beginning, the stiffer the anchor material, the higher the loads. This is because it can stretch less, so the angle can reduce less. And also for tension, they are strictly correlated. The higher the tension, the lower the loads, because the higher the tension in percentage naturally, because the higher the tension, this angle will decrease more, the higher the tension. And I have to say that if these all four rules were to apply simultaneously, it will be a mess, because mathematically it's difficult, and also from our mind, if you have to look at an anchor and think of all these four at the same time, you couldn't make it. But we were lucky, because there's a thing I call the simplicity, because of these four things, of these four rules, the tension and the elasticity effect, if the angle between the span sets, the more external ones, is lower than 80 degrees, these effects are negligible. They're like, you cannot see any difference between a sling or a climbing rope or 1 kilonewton tension or 10 kilonewton tension if you have an anchor lower than 80 degrees. So the only thing that matters are alignment and length. So you can focus on all that. And in our highline anchor, there are really few the times that I see anchors really, really wide. So keep in mind that we can focus on only just these two. So you just can look at the geometry. Thanks to that, we can use approximation because all the formulae that we're explaining, for example, this, but also that we're explaining this, can be used much simpler formula because all the concept of elasticity and tension can fall out. Imagine having 4 variables and they become 2, just 2. That they are also the same thing because they are a geometrical variable. So we are really lucky in that. And also, if you want to do a program or something, for example, an app, that can help you maybe just taking a picture of the anchor or just saying you can say where are the bolts. You have not to add the tension, that is the line, the elasticity of the material, that are 2 parameters that you almost never know, mainly the elasticity. Finally, there's equalization. And the equalization, the good news, as I said, is that it can always be achieved. And it can always be achieved in any anchor design, symmetric and asymmetric, but the number of branches must be higher or equal to 3, because as you can see, in this case, we cannot have it, and in this case, we cannot have it. Sure, in symmetric anchor design, you can always achieve it. 1 bolt, 2 bolts, 3 bolts, as many bolts as you want. But if you have asymmetric anchors, the 2 bolts system cannot hold the equalization. So the most important thing when you look an anchor is alignment of the branches and length. So remember that the internal branches have always to be longer to be equalized, and the more if there is no symmetricity, the more branches closer to the tension line, the higher the load it will carry. A last type of anchor that I wanted to talk about is the one that has extracting bolts. Imagine a flat surface and you couldn't bolt on the side, so you must bolt on the flat surface, and you have extracting force. In this case, we can talk about what is the best way to bolt, which is the best pattern, but for usage, for highline, let's say, like a personal opinion is that I prefer the hinge, everyone aligned, but only because it's not good from the force point of view, but it's good for you when you start walking towards the anchor, because the anchor function like a hinge, and all the branches carry a load. Maybe it's not the same load because they are not equalized, but they all carry a load. While if you do, for example, 1 bolt higher, 1 bolt lower, as these all things moves, you will have branches completely with not load. So maybe you can end up with only 1 branch, only 1 bolt in extracting mode carrying all the load. So this was the end. If you have any question, I will be happy to answer. And if you are more into the mathematical stuff and you want to know more, I wrote 2 papers about that, and I can link them for anyone that can want to read it. So here it is. Okay. You share the link here for papers.
Presentation, so we can look over again. It was quite a lot of information.
Yeah, I know.
You can just watch the video again.
Okay. I don't know if I can upload the file here in the chat, but I will try.
If you send it to, I'll post the email. If you send it to me, I can just post it on the page straight away.
Okay.
Hi, Lorenzo.
Yeah. Hey.
Can you hear me? Okay.
Yeah, I can hear you.
Yeah, great work. And
thank you.
Did you have a look about redirection or end frame, like how much impact it has to the force on the bolts, like when you have a redirection that reduce the force that you have on each bolt because of the redirection of the force in the redirection. And also if you have I mean, if you are on an edge, I mean, that's a redirection too. I don't know if you get it. So yeah, you can have some force redirected to the ground because it's on it. So I don't know if you have had a look on that or.
Yeah, that's a really good question. I thought about that. If you have a redirection, as you said, there's a percentage of the line tension that is transmitted to the ground thanks to the A-frame, or as you said, if you have the anchor on a ledge, you have part of this load that will be held by the, let's say, the corner of the ledge. Yes, it's true, but in fact. This study was imagine what I call the line tension, imagine there's the part of the tension that the anchor is suffering. That's true, you have a part of this tension, so that no, it's not the entire line tension that is taken by the anchor, but it's part of the one directed to the anchor. Yeah.
Yeah, and yeah, my question was in fact, if you know, like the impact, like the percentage or something like that, depending on, I don't know, maybe the angles. But yeah, it's mainly the angles.
Okay. Sorry. No, I never made this calculation, but now that you mention it, I will make it.
That's great.
It's really interesting.
I had a question in regards to the those 2 factors. You said we could basically ignore if it was less than 80 degrees.
Yes.
I'm assuming one of the scenarios where that would come into play is, say, throwing a sling around a large boulder, and the sling only just makes it around the boulder. and then that, and then the angle generated is extremely large.
Yeah, yeah.
So would your recommendations on that then be to use something more elastic with more stretch, obviously with ample rope pro, rather than a static material?
Yeah, the fact is that the phenomenon is very non-linear. So yes, naturally, stretch as a higher stretch as a key component, because you have to always imagine that you have this angle of the anchor of your anchor that when it's unloaded, that is, for example, 160 degrees. What you want is to decrease that angle the best way possible. And if you don't have enough material, for example, as you said, you have a sling that perfectly fits the boulder, you must have really elastic material, real elastic material. So as it stretch, it can become a smaller angle. Remember all of this in a static in a static world, because if you have, for example, movement of the line, more elastic means also more movement, so more friction. While static materials is the opposite. So this is what Sarah was talking also about before, that with slings you have lower stretch, and so you have, while, for example, a guy is bouncing on someone is walking on the line or surfing, you have less stretch. If you have a more elastic material, you have this movement that continue to abrade, for example. But yes, I would say a more elastic material. But first, I would say bring more gear.
Yeah, definitely. Yeah. Thank you, and great presentation, by the way.
You're welcome. I'm sending the yes, this too. And then also in the documents, you can see that I didn't talk of that here, but all the graphs and all that, you can see that the elasticity and tension, also I would say 90 degrees, you can push yourself to 90 degrees. They have nothing to say, nothing different. They don't add anything, any compliances to formulae of our anchors. So only if you push yourself higher than 90 degrees, you have problems to predict this behavior. You can still predict that, but it's not like a simple formula, but it's a much more complicated formula, and you need a computer.
Hello, Lorenzo.
Yeah.
I was thinking on this anchor that you comment before, like that was comment before, like you have a boulder and you can barely go around with a span set.
Mm-hmm.
I was thinking like as soft shackles don't suffer from triaxial loading, if you have like a span set like barely reaching it, how good enough would that be to make the connection there with a soft shackle? Because you still have the wide angle, but
yeah, it's true. You still have the wide angle. It doesn't suffer from triaxial loading, but it doesn't matter because their angle still there is. So if you, for example, have a 1 kilonewton force of the line with this big angle, I think, I don't remember the graphs by memory, but it depends on the material of the anchor, but it becomes like 5 more times or something like that. So if you have 1 kilonewton, you will find yourself with 5.
Okay, so it's a good way.
It's a good way to make the connection, because so the soft shackle is a good strong point. But anyway, all the anchor will suffer, the 2 branches of the anchor that are really wide will suffer a really high force.
Okay, okay. Thank you.